Students, I'm Praveen Sebastian Paul. In this lecture, we are discussing the logical circuit for a 4-variable K-map for a POS. So, my dear students, in the last lecture, we had discussed the 3-variable K-map logical circuit. And let us consider our example. This question was actually solved in lecture number 87. Our question was, simplify the function a plus b plus c bar plus d into a plus b bar plus c bar plus d into a bar plus b bar plus c bar plus d into a bar plus b plus c bar plus d into a bar plus b plus c plus d into a bar plus b plus c plus d bar into a bar plus b plus c bar plus d bar into a bar plus b plus c bar plus d. So my dear students, in the lecture number 87 we had discussed in detail about how to solve this problem. While reducing this function, it can be reduced in max term representation as pi of 2, 6, 8, 9, 10, 11, 14. That is, the given function is pi of 2, 6, 8, 9, 10, 11, 14. And the K-map representation for this given function is shown as in this figure. So this K-map can be reduced as two different code. The first code is C bar plus D and the second code is A bar plus B. Thus, the final POS for this given function is C bar plus D into A bar plus B. So my dear students, the given function can be represented in max term as pi of 2, 6, 8, 9, 10, 11, 14, and it can be reduced to POS as C bar plus D into A bar plus B. So while analyzing this particular function, we can see four independent individual variables, and the final product term has two terms, and each of these terms has different variables which are summed upon. So the summing or addition can be implemented by using the OR gate, and the multiplication can be implemented by using the AND gate. So my dear student, the POS circuit can be drawn with the help of AND as well as OR gate combination. So here in this given function, we used four individual variables. Thus, we have to consider those four variables. Firstly, we are considering the variable A. The A can be converted into a complement by implementing or introducing a NOT gate. Here the A is represented in blue color and a complement is represented in purple color. So my dear student, the next variable is B. The B is represented in light green color and the B complement is represented in dark green. The B complement is generated by knotting the variable B. The variable C is represented in yellow color, and the C variable is given to the NOT gate, and the output of the NOT gate will be C complement, which is represented in red color. And our fourth variable is D. The variable D is represented in black color, and the knotting of this variable D will produce D complement, and the D complement is represented in brown color. So my dear students, next what we have to do is implement the individual terms of POS. The first term of POS is C bar plus D and the second term is A bar plus B. While analyzing the first term, C bar plus D, the implementation of this term can be done by inputting C bar as well as D into an OR gate, and the output of this OR gate will result in C bar plus D. So we are introducing our first OR gate. The input of OR gate is C bar in one terminal and D in the second terminal. So the output of OR gate will be C bar plus D. C bar is represented in red color and D is represented in black color. So the second term is A bar plus B. So we have to use the second OR gate. The input of the second OR gate is A bar, which is represented in purple color, and the second input is B, which is represented in light green color. So we are providing these two input into the OR gate, and the output of this OR gate will be A bar plus B. And finally, for generating the POS, what we have to do is multiply both these outputs, that is we have to introduce an AND gate, and the input of AND gate should be the output of these two OR gates. So finally we are introducing the AND gate. The input of AND gate is C bar plus D in the terminal 1, and in the terminal 2 we are introducing A bar plus B. So the output of the OR gates are given as the input of the AND gate, and the output of the AND gate will be C bar plus D into A bar plus B, which is equal to the POS what we are requiring. So my dear students, this is how we are generating or representing a logical circuit for a POS equation. So my dear students, hope you had understood this topic. So dear students, kindly go through the assignment question. Our question is, draw the logical circuit for the function f of DEFG is equal to pi of 0, 1, 4, 5, 9, 10, 11, 14, 15. So my dear students, hope you had understood this topic. So dear students, in the upcoming lecture, we will discuss in detail about flip-flops and latches. So as a glance, these circuits, that is flip-flops and latches, are used in a digital circuit as memory units. So now we are going to discuss about the memory unit from the upcoming set of lectures. So my dear students, see you soon. Until then, goodbye, thank you, and all the best.